All right, welcome everyone to this video here for lecture day number 4, if you will, according to the calendar, right? In this video, we're going to talk about real gases and the equations of states that describe these gases. Specifically here, we'll talk about virial gases, and in the next video, we'll talk about van der Waals gases. Okay, so right, if we want to write the equation of state of a real gas, we can actually write it in this form, okay, where it looks just like the ideal gas, but there's this extra factor z here, okay. Z, right, for an ideal gas is equal to 1, right, and we get our ideal gas law back, okay. But for a real gas, z is not equal to 1, and it's not constant, and it changes with pressure, volume, temperature, right, of the gas, and so that z can be a function of, say, pressure or volume, okay? And so what one can do is what we can do here is we can expand z as a power series in terms of pressure or volume, right? As a reminder, right, a power series is something like 1 plus ax plus bx squared plus cx cubed plus so on and so forth, right? That is a power series of x, right? Where it's just a series of functions, right? Series of values of x to different exponents, okay? So I can write my equation of state for my gas in terms of this power series, in terms of pressure, okay? But I can also do it in terms of the molar volume, right? So notice here, right, that pressure is multiplied by P, while molar volume, we have the inverse of the molar volume, okay? So 1 over the molar volume, 1 over the molar volume squared, 1 over the molar volume cubed, so on and so forth, okay? Now, in these equations of states, these are called the virial equations of states for a gas, okay? And B primes and C primes and B's and C's and so on are called our virial coefficients, okay? Now, note that this is the first virial coefficient, and it's always equal to 1, okay? So B prime and B here are referred to as the second order virial coefficients. C prime are the third order virial coefficients, and so on and so forth, right? The first order virial coefficient is always equal to 1, okay? And then beyond that, it's some constant B, C, D, so on and so forth, okay? Some examples of the second order virial coefficient, right? Again, that B value, okay, in terms of B over Vm, right? That virial coefficient, right, for different values, right, we see at different temperatures has negative values here, or potentially some positive values at higher temperatures, okay? That negative value, right, if we remind ourselves from the previous slide, right, the equation of state PVM equals RT1 plus B over Vm, right? Our molar volume is always a positive number, right? While B here, okay, B is some constant, right? Notice that at 273 Kelvin, for all these gases, B is a negative number, okay? B being a negative number here, right, means that I'm sort of subtracting off the absolute value of that B, okay? Which means, right, that this term here, right, again, is related to Z, right? So in this equation of state, right, Z equals 1 minus the absolute value of B over Vm, okay, in our example at 273 Kelvin, okay? So you see our compression factor Z is always less than 1 for each one of these gases, right? And what that's saying is that for each one of these gases at 273 Kelvin, right, attractive forces are dominating, right? And it will have a compression factor of Z less than 1, meaning its molar volume will be less than that of an ideal gas, okay? While at 600 Kelvin, certain molecules like argon and neon, okay, all of these molecules, by the way, their dominant intermolecular force is dispersion forces, okay? So for the smaller molecules like N2 and argon here, right, at high enough temperatures, now the repulsive forces are starting to dominate, because at high temperatures these molecules are colliding more often, and when they collide they get closer together during that collision, and so they're starting to repel each other more. And so now for a positive value of this virial coefficient B, our compression factor will be greater than 0. Okay, so right when B is less than 0, Z is less than 1. When B is greater than 0, Z is greater than 1. Okay. So this virial equation of state is a very exact equation of state, exact description of the equation of state for a gas. Okay, but these coefficients have to be determined in the lab through very careful analytical work in the lab to determine what these virial coefficients are. Okay. One way you can look at getting, say, that first order virial coefficient, right, is the fact that if we look at the slope of our compression factor of our gas, right, in the limit of very low pressure approaches this value B prime, right, or for very, very large molar volumes, it approaches the value of B, okay, right. And you can look at that because when you take the derivative of the compression factor Z with respect to pressure, okay, taking the derivative of 1 plus B prime P plus C prime P squared, so on and so forth, right? And so that first part of the derivative is just 0, and then derivative of P with respect to P is just 1, and so you're just left with B prime here. And then the rest of the terms depend on P, so when P approaches 0, those all go away, and so you're just left with kind of B prime. Okay, so this is one way you can measure these coefficients, right? These virial coefficients for a real gas. Okay, so again, just kind of solving that, right? Note again that, right, we talked about at the beginning, the equation of state of our gas is RT times this coefficient Z, right? So this compression factor Z is just this expansion in terms of pressure or molar volume. Okay, take that derivative, right, and then now in the limit P goes to 0, right, these terms all will drop. Okay, and so we're left with just dZ dP is equal to B prime at very low pressures. Okay. Right, and then here talking about kind of the boil temperature. Okay, the boil temperature for a gas is the temperature in which the compression factor Z is equal to 1 for the longest amount of pressure, the most type of pressures, if you will, right? So you see here, right, that this equation is this line, right, the middle line here is closest to 1 for the longest at these low pressures, right, while at high temperatures or lower temperatures below this boil temperature, right, the compression factor either quickly drops below 1 or quickly goes above 1, right? And so the boil temperature is a temperature in which the compression factor stays equal to or very close to 1 for the most amount of types of pressures and things of that nature. Okay, and so that is our description of virial gases, right? We should keep in mind what those virial equation of state is, okay, and just the fact that it can be expressed as a power series of pressure or a power series of the inverse of molar volume, and which power series we choose can kind of depend on the problem.